Welcome. Today we're going to talk about the k-nearest neighbor classifier. It's a very simple method which is very easy to run and very intuitive, and it's often a good baseline before trying more complex methods. So before we get into talking about what the k-nearest neighbor classifier is, let's talk about a very important concept in machine learning, which is the Bayes optimal classifier, the Bayes classifier. This Bayes classifier is kind of a thought experiment in the sense that in general, you're not going to be able to implement the Bayes classifier. It's something which requires more information than you would realistically have, but it's a good baseline to just understand what is the limit of how well you can do information theoretically. Say, if somebody told you some secret information, or you had infinite amounts of data, how well could you do? And we'll see later that in a certain technical sense, the k-nearest neighbor is able to compete with what is known as the Bayes classifier. So let's talk about what the Bayes classifier is. Recall that our goal when we're doing classification, so today we're going to be just focusing pretty much on binary classification, but our goal is in general to be able to output a function f which minimizes the probability of being wrong. So the goal is to find some f such that fx, the probability that fx does not equal y, is minimized. So minimize this, where we have that x and y are drawn according to the distribution D. So that's the goal in general for when we're trying to do machine learning, or classification in particular. So the thing is, what could we do if we happen to know what D is, the distribution from which we're drawing these points? Well, the best possible thing I claim is the following, choosing the following classifier, and we'll call this f star, which is the Bayes optimal classifier. So the idea is, remember, any classifier takes in a point x and makes a prediction. And the prediction that we're going to make is the following. We essentially take this point that we have, and then we see sorry, let me just say what this probability is over. Y drawn from the distribution D of y conditioned on x. So what this means is essentially, what we do is we take, given a point, what we do is we take that point, we look at what the distribution of y would be, where y is drawn from the distribution D, but conditioned on receiving this x. And then we essentially pick the probability, we pick whichever probability maximizes the chance of it being right. Yeah, so this is the Bayes optimal classifier. It might seem a little bit unintuitive, but let me give you a few examples just to draw some illustrations. This might be kind of simple, but let me draw some coordinate axes. I guess we don't need some coordinate axes, so let me just draw it freehand. So imagine we have some space, some space here, where anything falling into this is going to have probability, let's say, 1 of being 1. So anything within this, let me change back to this. So for any point that lands in here, the probability that y equals 1 conditioned on x equals 1 for all x in this space. Let's call the set S. Yeah, let's suppose that's that. And then anything outside that space, say like in the whole rest of the space, then the probability of y equals -1 conditioned on x equals 1 for all x not in S. So suppose we had these two cases where basically if you have a point that lands in this, then it's going to be a 1, and any point that lands outside this is going to be a -1. Well, the Bayes optimal classifier, which recall knows these probabilities, it would be able to easily get perfect accuracy on this, in the sense all it has to do is for any point x which is in the set, which it magically knows because it's very powerful, it would predict a 1, and anything outside that set it would predict a -1. Just because that's the most likely value for the label, in fact, with probability 1. Now, this is kind of ridiculous because for any given point, it seems unlikely, or in many cases, it might be unreasonable for things to be exactly like this. Like, we're not going to have some hard threshold where anything within this is going to be a 1 and anything outside is going to be a -1. So while in this case, the Bayes optimal classifier can get exactly 0 error, there's more reasonable cases where other things might hold. For example, imagine there exists some half space or something, and then things which are kind of very far on this, like they're just a poor caricature, but like, let me say like things over here, these are going to be very likely of being a 1, and things here, they might be like less likely to be a 1. Hopefully my sort of random scribbles will kind of make sense when I explain. But what I'm trying to say here is, suppose there exists some like linear classifier where things, the further they are across the line, then the more likely they are to be whatever. For example, here, maybe the probability that y equals 1, conditioned on being sufficiently far from the line, is, say, greater than, I don't know, 0.7%, or 70%, and things here, in this sort of space here, that the probability that y equals 1 conditioned on x is, say, equal to maybe 0.6% or 0.6, 60%, whereas things here would be like the opposite way. This would be, say, equal to, I don't know, 60%, that's equal to -1, and so on. So for this type of thing, the idea is that even with the perfect knowledge of the point, things could go either way. Like, for example, if you have a point that's right here, there's maybe a 60% chance that's going to be an orange, but there's maybe a 40% chance that it's going to be a blue point. So while it's more likely that it's an orange, there's still some, I guess maybe a better way of drawing this picture would be to have some sort of leakage over the boundary, because like the idea is that there's some chance that on either side of this, it'll be the opposite color, but it's like less likely the further you get ahead. For example, over here, there's like very little orange and very little blue over here. So hopefully that makes sense, where in this type of setting where we don't have a perfect probability 1 chance of whatever the correct label is being assigned, in these types of cases, then the Bayes optimal classifier would not do quite as well. Yet, nonetheless, it would still be really still the best we could do, possibly, even if we knew the distribution. There's nothing really better than that that's possible, and there's proofs of that which I won't go through, but you can look it up. Let me just show you the most extreme case, the kind of silliest case, like sorry, let me, I've drawn all of these together, but let me separate into a third example, which I'll draw over here. Yeah, let's suppose that we just have some space like this, and we don't really know anything better than a random guess. Like, let me draw this and like draw this. And all I want to say is that suppose in this case we have probability that y is equal to 1 conditioned on x. This is equal to, say, 0.5 for all x in the set. If this were true, then that means that the position where it is in the space, it doesn't really tell you anything about what the label will be. It's a 50-50 chance. It's just a coin flip no matter where you are. So therefore, the Bayes optimal classifier will have the most possible loss, but in fact, there doesn't exist any classifier that would be able to do well on this. Good. So I hope this all gives you some idea of what the Bayes classifier is. Let me just write out a convenient way to understand what the overall loss is for a Bayes optimal classifier. So we can just rewrite this as, for when you plug in the Bayes optimal classifier, this is going to be equal to, I guess, let's just plug in f star, because that's the optimal classifier, which we defined up here. Of x not equal to y. And let's sort of integrate or marginalize this out. So this can be also rewritten as integral over all possible x times of probability of seeing x and times probability if x does not equal y conditioned on x. So what are these probabilities over? This is kind of important. So this is going to be the probability space of where we just draw x according to the distribution d, but just the marginal corresponding to x. And for this one, we're going to draw y, again, from the same distribution here. It's going to be the distribution d of the marginal of y, but conditioned on the value of x. And now the convenient thing is this is just going to be an expectation when you draw x from the distribution x, because we have some function which is integrated against the probability of x over the entire space of x. So this can be rewritten as the expectation of x drawn from d of x. Again, this just means the marginal of x. And this can be written as, this can, oh, sorry, there should be a not equals. This can be rewritten as 1 minus argmax of probability y equals c given x, where this probability is over, again, y drawn from the distribution d of y conditioned on x. Cool. So this is a fairly simple way, and you can kind of match it up with these different cases. You can see that here, when you have anything in this very simple case, then you're going to have that argmax of this probability is going to be 1. So you have 1 minus 1, which gives you 0 loss. Here, in this case, you have that this argmax is going to be 0.5, and therefore this will be like 1 minus 0.5, and then this will be expected, the loss will be 0.5, and here it'll be something in the middle. Good. Yeah, one reason I hesitate here actually is because it's not argmax, because argmax over c would give you what the class is, but really what we should be doing is just the max, because we care about max over c, because that tells you the value of the probability. So this essentially tells you the probability that your prediction is going to be right, this max over c probability, whatever. And 1 minus this tells you the probability you're wrong. So yeah, hopefully that's an easy way to see it. 1 minus this max is the probability you'd be wrong at any given point x, and you just integrate that probability of being wrong over the entire distribution of the space. Good. So this is the Bayes optimal classifier, which is an important concept. And like I said, this is an impossible algorithm in the sense that it requires you to really know what the distribution is over the space, which is unrealistic. You can't do that unless maybe you have infinitely many samples or somebody told you. It's not realistic. But it's nice because it's a kind of baseline, a baseline, if you will. But no, it's a good baseline. And the idea of K-nearest neighbors is somehow, in some sense, we're trying to approximate that. Like, let me tell you the key principle behind let me tell you a key quantity that we used here. The key quantity we used here was this function right here, this sort of probability that y is equal to a particular label conditioned on x. So the key principle that K-nearest neighbor operates on is the following. Remember when I said before that whenever you use a type of machine learning model, there's some sort of implicit assumption you're making about your data. And the implicit assumption you're making here when you run K-nearest neighbors is the following. You're essentially trying to make the following, you're essentially making the following assumption about your data. You're saying that, let me see this. The following, you're saying the probability that y is equal to c conditioned on x for, I guess, y drawn from d of y given x is close to the probability that y is equal to c, conditioned on x prime, and let me just write this. These two distributions are close when x and x prime are close. So this is the key principle and assumption we're kind of implicitly making whenever we run k nearest neighbors, in some sense, that if 2 points are close in space, then they should kind of have similar label distributions as well for that point. Yeah, points are close to, label the points are close by when the points are close. And okay, so that's the principle that we're doing. And what is the algorithm itself? Like I said, the algorithm is a very, very simple one. You can see it written here. It's like 4 lines. Let's walk through the algorithm to see what's going on. So the idea is the following. We have some data set, which is input, which is xi's, yi's, which are in the space. There's endpoints. And what we're given is a single new instance, a new point x, which is in the space, and we want to predict its label. And importantly, there's a hyperparameter k, which tells us how many neighbors we're going to look at. And the goal is to output a single prediction of that point's label, y of x. So now what we're going to do is, given this new point, we're going to go through and compute all of the distances. So we compute the distance between this new point x and the distance between that and x1, between x2, x3, x4, and so on. We're going to compute all the distances. We're going to find the closest k points, the smallest, the indices of the smallest entries in this sort of set of distances. And somehow we're going to aggregate the labels according to those things. So to say this maybe in common parlance, what we're going to do is we're going to find the k nearest neighbors and make a prediction based on their labels. So let me give you a brief illustration of maybe what this might look like. I'm going to make an example on the fly. So let's suppose we had something that looks like this, something like this, and then we have points over here, I don't know. And then we had some minuses, minus. Yeah, that's probably good enough. So this is, say, some data set with some pluses and minuses in space. And what we're going to do is, suppose we're given a new point. A new point is, and let's set the hyperparameter for now, just for this example, k equals 5. Good. Let me just, for the sake of illustration, throw in a few more points. And yeah, so right. The idea is that suppose we're given a new point, which is right here, and we're asked to predict what is the label of this point. So what k nearest neighbors does is it takes a look at the 5 nearest points, because k equals 5, and that's these 1, 2, 3, 4, 5 points. These are clearly the 5 closest points. And it makes a decision based on what their labels are. So we see that when and the most common way to do this is just by looking at the majority label. For example, here we can see that there's 3 which are +1s and 2 which are -1s in terms of the labels. So we will predict that this one is a +1. Now, yeah, that's about it. It's very simple. Now I'm going to make a bunch of comments about different aspects of this algorithm and this definition. So let me see a few things that I want to comment on, and I'll try to list them as I go through them. Yeah, one thing I want to make this is a non-parametric method. And what do I mean by that? This is kind of, remember when we were talking about all these other things such as perceptron or linear regression, the idea is there's some underlying parameter vector that we're trying to estimate, which has some fixed number of parameters, say d, which is the dimension or something like that. Whereas this is a non-parametric method, meaning there's no type of underlying probability, some underlying parameter vector which we're trying to learn. So this is called a non-parametric method. What else? I mention, there's other things I want to mention as well, which is, for example, I said, notice how it says here distance. And when you kind of think about this, like distance, okay, you just think the nearest points. but let's just mention the fact that often a natural distance to use is L2 distance. So let me just remind you of a few of these distances which are important. So if we have a point here, then the L2 ball, or the L2 distance, is the L2 ball consists of something that looks kind of like this, of whatever radius, and anything that's within this ball is at L2 distance less than or equal to r. But sometimes, depending on which setting we're in, other types of geometries might be relevant as well. For example, let me show you that. Let me say that this is the L2 ball. Let me draw another type of ball, and this is what's known as the L1 ball. So this is the L1 ball of radius r. And the idea is, like, this is, it's just, it might not look like a ball to you, but the idea is that if you look at the L1 distance between any 2 points within this, then their distance is less than or equal to r, or sorry, I guess the 2r, because this is the radius. Yeah, the idea is just sometimes different geometries and penalizing things in different ways can sometimes be better or worse from one another. And as a last geometry that I'll mention, for example, is let me draw the L infinity ball. So this is the L infinity ball, where the idea is that if in any coordinate, if in all coordinates the points differ by less than or equal to like r or 2r, then they're kind of in this same ball. So hopefully this at least illustrates the kind of different distances you might consider, and different ones might be better for different problems depending on what specific problem you're trying to solve. Good. So these are a few comments. Let's talk a little bit more about sort of what the complexity of this problem is. So one thing we can say about the complexity of this problem is that it's like what is the when we're training the classifier, what's necessary? Well, when we're doing training here, it's really trivial in the sense that we just store our data set, right? When we look at this algorithm, there's nothing special about it. We just store it in maybe a list or whatever, an array, nothing fancy. So the training takes essentially 0 time. You just store it. You don't have to do any sort of processing. But the thing is, the space complexity is a little bit worse in the sense that it's O of n times d space. And the reason is because we have to store our entire data set when we're training. For other things, note, for example, like when we're training linear regression or the perceptron, we only need to store the parameter vector w. So in other words, after we train our classifier or train our model, then we can throw out the training data. We don't have to worry about that anymore. Whereas with K-nearest neighbors, then you always have to store the training data set. That's the training time and space required. But at test, this is sort of a trickier part in the sense that here, when you do the testing, you have to take O of n times d. Let me say it naively, ndk time, which can be improved to O of nd time. And let me tell you why this is. What is the test algorithm? Basically, what you do is the most naive possible way to do it would be to look through your data set, which takes O of n time. For each point in your data set, you want to compute the distance. So that doing those two things together, because it's d-dimensional, that takes O of nd time. And then essentially find whichever one's the closest, then you remove it and repeat. So if you do this total k times, because there's k points that you want to find the k nearest neighbors, then it'll take O of ndk. But if you're careful and you're smart about it, then you can actually do this in O of nd plus k time. So that's something you should probably do when doing this carefully. But yeah, nonetheless, it still requires a lot of space, O of nd space. So this is not super great when it comes to answering things on the fly if you care a lot about your test inference time, because it takes O of nd time. Basically, you have to look through your entire data set, and we generally think of n as being a pretty large number if you have a large training set. Cool. Can you do better? The answer is yeah, sometimes you can do better. And what I drew here is what's known as well, I didn't draw this, I found this picture online, but this is what's known as a Voronoi diagram. And this is something you might have heard of this in, say, CS240, but this is a nice data structure you can pre-compute, which is useful for the specific problem of one nearest neighbor. So where, in particular, you want to basically find just what one point is closest to each test point, and then you can pick the corresponding label. For example, it gives a very fast way to look up. For example, any point within this cell, well, the closest neighbor is this point right here, and so we'd pick whatever label this point has. Anything here, we would pick this one, and that would be the label. We go with whatever label it has there. So this is a way to do a very simple type of nearest neighbor, which is just one nearest neighbor. But the thing is that this is, yeah. So what can we say about this approach? Well, we can say that this is faster in the sense that the lookup time, the test time, Voronoi diagram, they would have test time of O of d log n. This is much faster. The downside is that wait, let me just say time. But the thing is, the space requirement is something much worse, which takes n to the order of d space. So now this is okay maybe if you're in just a low dimensional space. For example, if you're in 2 dimensions, then this is great because, or this is maybe good enough because it gives you very fast lookup time. It'll just be log n time, but it'll be at least quadratically much space in order to store it. So yeah, this is great. This is pretty good in low dimensional settings, but if, as you said, d larger and larger, then it's not great. So yeah, it seems like generally nearest neighbor classifiers can it's not really in general possible to get beyond this like linear scan type thing in general if you want to solve it exactly and stuff. There's other things such as, I'll mention, there's approximate nearest neighbors. And this is these are algorithms which are meant to do some sort of approximation and then do faster things there, but I won't get into that. But those are ways that we can get around these barriers, which just to sort of summarize, things either take a long time at test time, O of nd test time, but either that or they take a lot of space, and even this is just for the simple case of one nearest neighbors. Cool. So yeah, we've talked a little bit about the algorithms. Let's talk a little bit about the effect of k, which is a hyperparameter. To give some intuition about the effect of k, let's revisit the example which I just did a little bit above, right here. So let's take a look at this exact same test point that we had, where we looked at the k equals 5 nearest neighbors. And we saw that it's going to be labeled as a +1 according to this rule. Now, what happens if we increase or decrease the value of k? So you can see actually, for example, it could flip sometimes. For example, if we set k equals 3, well, it's a little bit hard to say when eyeballing it. Maybe the 3 nearest neighbors are these 3, maybe something like this. And in which case it would be labeled a -1 instead of a +1. Similarly, if you take, so that's if you take k smaller. What if you take k larger? Well, for example, if you took k to be equal to, say, 5, 10, 11, if you took k to be equal to 11, then it would be the entire set, and it would just be looking at things, basically, what is the majority class? And in the overall data set, the majority class is -1s, so it would also be -1. So you can see that there's a certain type of tuning, and I'll show it with some other examples a little bit later about how this can go sort of both directions. You want to choose just the right k. If you choose something maybe too big, then it'll something too big or too small, then it'll go wrong one way or another. Okay, so let's see another example. So like here's an example which is taken from Introduction to Statistical Learning. This is one of the books on the website, on the course website, and you can see what's going on here is there's some sort of there's some data set which is generated. And what are the different things? Well, these are, I guess, plus ones, the blue ones are minus ones, and see this purple line here. This purple line is the classifier which the Bayes optimal classifier would give. So they haven't derived it here, but that's kind of what's going on. If you actually derived it and found out what the Bayes optimal classifier, based on what the underlying distribution they had is, that's exactly what it would be. And now what they've done here is they have computed the black line here. The black line is the k equals 10 nearest neighbor classifier. You can see that this is pretty good. It's pretty close to the the Bayes optimal classifier. Of course, there's some things which it gets wrong. For example, things over here. But really, if somebody didn't tell you what the label of this point was, you'd probably think it's the blue point as well, -1, and vice versa for things here. So that's k equals 10. But what happens if we take k to be smaller or larger? And we can see that with these examples here, which are on the same data set, but just setting k equals to 1 and 100. And you can see what happens, first of all, when we take k equals 1, then perhaps it kind of looks too myopically, because say a point right here, sure, it's right for this specific point here, that this one in particular is going to be a -1, it's going to be a blue. But say anything right next to it, should that actually be a -1? It seems more natural that anything in these neighborhoods around these should probably be orange based on more global properties. So this is looking a little bit too locally. And indeed, you can see that the decision boundary that it comes up with of whether to label something as a plus or -1, this is not as good at tracking the Bayes optimal classifier, whereas the one above was somewhat better. And let's go the opposite direction. When we set k to be very large, say k equals 100, then it also doesn't perform very well, because you can see that the decision boundary becomes more like a straight line. And there's many points over here which are classified incorrectly, many points over here which are classified incorrectly. Yeah, so really want the middle sweet spot. I'll mention that actually, if you take k to be large enough, if it's equal to n, then it just degenerates into predicting the majority class on any point, because it'll just look at all the points and see, are there more plus ones or minus ones, and then make a decision based on that. So definitely taking it way too large is not a good idea, but taking it too small is also not a good idea, because it kind of ignores some of the more global features, or it looks too locally. So yeah, you have to make sure you pick the right k, and the appropriate and principled way is just to do hyperparameter selection in the ways we've discussed before, for example, using a validation set, or by performing cross-validation, or things like that. These are appropriate methods for selecting the value of k. Good. So this is k nearest neighbors classifier. It's a very simple algorithm. The question you might ask is it any good? Does it work? And surprisingly, it can be a very good baseline in a number of settings. So let me talk about, does it work on MNIST, first of all? And before we talk about does it work on MNIST or not, let's talk about what MNIST is. This is a very important data set, which any person working in machine learning should be familiar with, because it's kind of the first data set that a lot of people study. And you can see what it looks like here. These are images from MNIST. It's an image data set, and it corresponds with handwritten images of people writing the numbers 0 through 9. Now, let's tell you some more about this data set. There are 60K training images. There are 10K test points. And each image is going to be 28 by 28, which is equal to 784 pixels overall. And these pixels are going to be binary. Things are either going to be black or white. So this is different from color images, which maybe have 3 channels, which RGB would make it look like a color image. But here we're just looking in black and white images. It makes the problem simpler. So the goal is, given this training set of images, which are 10 different classes labeled 0 through 9, and then you're given a new test image, and you have to predict what type of what number it is. So this is, of course, very, very easy for humans to do. You know, you can recognize this as a 1, this is a 5, this is a 1, and so on. And it turns out that it's pretty easy for computers as well. So MNIST, like I said, is kind of one of the first data sets anyone will look at when studying any sort of machine learning algorithm. And, you know, the thing is, people have kind of moved away from it in the sense that really anything works on MNIST. In particular, let's see how some different methods work on this. So sorry, this is a bit small. Can I zoom in a bit? I apologize, but I don't know how to, so maybe here. All right, I don't know how to zoom in, but this is maybe as far as it goes. But okay, let's see. This is from a page, I think, maintained by Jan LeCun, which shows how different classifiers perform on MNIST. And so a perfect classifier would have test error rate 0, but say a simple classifier, and a linear classifier with a one-layer neural network, in other words, which we'll talk about a bit later, would get error rate 12%. So it would get 88% accuracy, which is pretty good for many machine learning tasks, but for MNIST, this is terrible because of the fact that MNIST is very easy. And in particular, to show you the power of k-nearest neighbors, you can see that by just using Euclidean distance and with some appropriate k. I'm not sure what k is for this, but you can actually get all the way down to 3% error. So this is really good. 97% accuracy via just doing very simple methods. This is already very good. You can do a little bit better if you switch, say, from L2 norm to L3 norm, which allows you to get it down a little bit. And you can do even better if you use k-nearest neighbors with some nonlinear deformation. This is kind of just somehow morphing the images in some appropriate way, mapping the images in some certain way, and then doing k-nearest neighbors on that. So these are pretty good. These are not state of the art, but for such a simple method, this is really good. In particular, maybe people like to throw neural networks at whatever problem they try to solve first. So say a 2-layer neural network with however many hidden units. This will get you, say, 5% error, and going to more complicated things like convnets will give you 1% error. But note that these are sort of comparable in various different cases with just the naive k-nearest neighbors classifier, and if you do it right, you can even do better than that. So just don't discount k-nearest neighbors as a simple classifier, which generally which may work very well actually for some simple problems. Okay, so that shows whether it works and when it does that it does work on MNIST, let's say. And as a last thing, let's talk a little bit about the theory and why we might expect MNIST to, or sorry, why we might expect, how well can we expect k-nearest neighbor classifier to work? Well, there are some theorems which we can say, but one of the important ones, which I'll just state, which I will not prove for you, is the following, saying how good is the one-nearest neighbor classifier. Well, let's say the following. Suppose n approaches infinity, so we take a lot of points. We'll revisit this in a sec. You might think this is kind of silly, but yeah, suppose we take n points going to infinity. Then we have that the loss of one nearest neighbor classifier, that is the probability that, sorry, if it draws a new point, what is the probability that it's mislabeled according to the one nearest neighbor classifier? This is going to be less than or equal to 2 times the Bayes loss, the Bayes optimal loss, times 1 minus L Bayes. So this is a theorem that's possible to prove. We're not going to go over it right now, but let me see. I think just to give you a reference for it. A reference for this is by, it's a kind of classic result because this is a very simple classifier, so people studied it for a while, but this is by Cover and Hart in 1967. A very old result comparatively. And let's see what this means. So remember what I said. The best we could ever hope to do is just doing the Bayes loss. Whatever that would get us, that's kind of the best we can possibly hope for. There's no beating that. And what this says is roughly that this is going to perform twice as, it'll get an error which is less than or equal to 2 times that. So this is pretty comparable to the Bayes loss. Let's look at some sort of extreme cases. Suppose, let's look, for example, if L Bayes, if the best classifier is equal to, it can perfectly predict things, then just plugging it in, that'll give you L, one nearest neighbor, is equal to 0. Yeah, so this is recall all the way from the beginning of today's lecture that that corresponds to this image where everything can be predicted perfectly by the Bayes classifier. Then the one nearest neighbor will predict perfectly. And let's look at the other end of the spectrum, where suppose that the Bayes classifier is just guessing randomly essentially for every point. Well, in that case, we also we essentially achieve that. So if L Bayes is equal to 1/2, then this will also get 1/2. Then, yeah, just plugging in, you can see it would give that. So in the extreme cases, it's actually going to match the Bayes classifier, but in kind of the intermediate cases where, yeah, in the intermediate cases, then it's going to be roughly, the upper bound that we have is basically twice it. So let's just give you a simple case. Suppose that this is equal to 0.1. Then this is going to be less than or equal to 2 times 0.1 times 0.9, which is equal to like, what, 0.18, I think. Yeah, that should be right. And so you can see that it's roughly a factor of 2 off from what the Bayes optimal classifier would give. So yeah, there's also more complex theory that we can say for when you have, say, k nearest neighbors to be 2, 3, or for general k. But that's just one sort of theorem that I wanted to say, and how we relate this to the Bayes classifier in the sense that this can be competitive up to a constant factor. Now, there's one especially very important caveat to this theorem, which is the fact that this big one here. This says that suppose n approaches infinity. So what does that mean when n approaches infinity? How big does n really have to be? If you just had infinitely much data, then there's probably a lot of good things you can do. And it turns out that there's a kind of no free lunch theorem, as they're sometimes called, which says that in higher dimensions, then you'll have to pay a lot in order to get down to a at all reasonable error. So let me give you an example from one of the other textbooks, which is in the book by Shalev, Schwartz, Ben David. This is the Understanding Machine Learning book. So let me just sort of informally state it. And this tells us about how nearest neighbors, or in general, there's some sort of cursive dimensionality, which is an important phrase. Essentially, what cursive dimensionality means, it's kind of not a, dimensionality. Cursive dimensionality is not a rigorous, like defined phrase, but it just means when you're in higher dimensional settings, then things become harder for some reason or the other. Maybe you need more data, something like that. But the demonstration of cursive dimensionality here is the following. So the claim is the following. There exists a distribution over 0, 1 to the d by 0, 1. Let's make it plus or minus 1, I guess, because that's what we've been using for labels. So that means there's a distribution over what's known as the kind of Boolean hypercube, like picture one of these things, but in higher dimensions, where each side length is 1, or drawing scale. So this is a 3D cube that I tried to draw here, and each point on this is, each point has its own distribution over the possible labels plus or minus 1. So suppose there exists some distribution over this, and where the Bayes error is 0. but any classifier given n less than or equal to, say, 1.5 to the d samples has error which is, say, greater than or equal to 1/4. So okay, let's this is a theorem which is, you can find it somewhere in this book. But let's see what it says it means. It means that there's some distribution over like this high dimensional space. So d is the number of dimensions, and the Bayes loss is 0. That means if you knew this distribution, then you could predict every point perfectly. Yeah, you'd be able. There exists some sort of perfect classifier which gets 0 error. But the claim is the following: suppose you don't know what this distribution is, and instead you're just given points, which is pretty much the standard case in any sort of machine learning problem. We don't know the distribution, but we just have points sampled according to the distribution. Well, if you have a classifier which is given less than n, which is given n less than 1 to the 1.5 to the d samples, then this will have error greater than 1/4. So what this means is 1/4 error is kind of a lot, like in the sense that we'd really like some error which goes down to 0. Yeah, this is just sort of an arbitrarily picked constant. We'd really like to have something with a very small error if we're taking a lot of samples. But the main thing here is that really, what is the threshold for being able to get around this theorem? We need n to be greater than or equal to 1.5 to the d. So the key thing here is that this is exponential in d, and if we want to get a good classifier, that tells us we would need at least 1.5 to the d samples, which is exponential in dimension, and probably more data than we could hope for if in say, if you have d equal 10, 20, 100 dimensions or something like that. Yeah, this is way too costly. So what does this kind of tell us? I mean, this was just a theorem for theory's sake, but like what can we understand about this? This kind of implies that these theorems about saying how well we approximate the Bayes classifier, these really either only apply in low dimensional settings or when the number of points gets very, very large. Otherwise, it's not really meaningful. And this theory kind of backs up what we see in practice in the sense that nearest neighbor classifiers often perform very well in, say, lower dimensional spaces. But as we get up to higher and higher dimensional spaces, things can really go bad and we don't necessarily get good accuracy. So it's often a better tool. It may often be a better tool in lower dimensional spaces. But yeah, that's everything I want to say about k-nearest neighbor classifiers. They're a simple baseline which often work very well, and you should try them as often as a first shot at solving a problem, rather than just picking something more complicated.